This is Formal Lab 3 by Shanna Hilborn, Shay Oswald, and Legend Kenny. To begin our lab, we wanted to look at the absorption spectra of dyes and the fluorescence of dyes. In the first part of the lab, we were given an unknown dye and had to find its absorbance spectrum to determine which dye it was from the two given dye absorbance spectra. In the second part of the lab, we were given fluorescein dye. Using the dye, we had to find its absorbance spectrum and the fluorescence spectrum. For the first part, which focused on absorbance, which is a measure of how much light is absorbed in a given path length, and the goal we decided was to find the absorbance pattern to unknown dye. The absorbance graph for the dye was then compared to the two known dyes. For the second part, we dealt with fluorescence, and fluorescence is the process of how molecules can have their electronic states excited and produce light as these molecules return to lower energy states. Our goal was to graph the absorbance of the spectrum of the fluorescein and the fluorescent spectrum of fluorescein. In part 2, we use fluorescein. This is a green dye that is used in planes. If a plane were in a crash in a large body of water, the water around the crash will turn green due to the fluorescein. Questions from our lab packet. How do spectroscopes identify an unknown sample using an absorbance spectra? Once spectroscopes identify the absorbance spectra of the unknown sample, they can compare that spectrum to another known spectra. How are absorption spectras different from fluorescence spectras? What are the critical differences? What are the same uses for each? Absorbance spectra is the wavelength of light that are absorbed by the objects. The fluorescent spectra are the wavelengths of the light that are reflected for chemical dyes. Fluorescence will be the color that the dyed objects appear to the eye. Absorption spectras are used to make a plot of our absorption and peak fluorescence of fluorescein. See discovery slides. So we then explain why a certain wavelength photon goes in a different wavelength, comes out of fluorescein when fluoresces. Some of the energy of the photon is being converted into kinetic energy, so the photon will come out with a lower energy and a higher wavelength. If a different wavelength of light comes out than goes in, is the energy still conserved? Explain. Energy is converted into kinetic energy, but it is conserved. Describe the critical steps in the setup to the fluorescence measurement. Why is it important to have a dark environment and the light source 90 degrees from the fiber optic cable? It should be dark so we can limit outside light being picked up from the fiber optic cable. Readings from 90 degrees allow the fiber optic cable to read only the fluorescent measurement because the white light of the flashlight is no longer shining directly at the cable. The dye is still fluorescing due to the flashlight still shining on the dye. So our experimental design for the first part, the flashlight and the wand of the spectrophotometer were both taped down to the table. First, we filled the cuvette with water and found its intensity per wavelength by placing it in between the flashlight and the wand. Next, we were given the cuvette with the unknown dye, and it found its intensity per wavelength by also placing it in between the flashlight and the wand. For the second part, the flashlight and the wand of the spectrophotometer were both taped down to the table. First, we placed the fluorescein cuvette in between the flashlight and the wand. This allowed us to find the intensity per wavelength. Next, we had to reposition the flashlight so it is now perpendicular to the cuvette. This allowed us to find the fluorescence spectrum. So some relevant models. We need to know what an electromagnetic wave is to do this, and an electromagnetic wave consists of an alternating electric and magnetic field, which you can see in the bottom right. And these waves can be affected by mediums because mediums cause a magnetic interaction causing the wave to be affected. Different permeabilities of mediums cause different changes to the wave which can be measured. Since certain properties can't change within a wave, such as frequency has to remain constant due to the law of conservation of energy. This means that the speed/wavelength is changed. The change in the speed/wavelength can be measured, and this is used to identify the medium that the light passes through. For part 1, we used the intensity data we found for the water cuvette and the unknown dye cuvette to find the absorption spectra for the dye. The intensity data of the dye cuvette was subtracted from the water cuvette intensity to find the absorption spectra for the unknown dye, which gave us this graph to the right. which is in blue. Now, the graph we found via our data closely matches the Lapidus dye absorption spectrum, which was given to us in the top. So the expected curve on the absorption spectra should not have any negative values, and our curve showed some, likely because it picked up outside light. For the second part, we used the data to find the graph, which the blue line represents the absorption spectra of the fluorescein. This was found by taking an intensity data from fluorescein and subtracted it from the water intensity data from part 1. The result of that is the blue line on our graph after the first peak on the blue graph does not completely match the given graph above. This is because the wand of the spectrophotometer likely picked up the light from the outside source in the room. The red line in the graph is the fluorescence of the fluorescein. The data was found by putting the flashlight in a different position, which was perpendicular to the cuvette and the wand of the spectrophotometer. The data we found for this closely resembles the graph given. The right side of the peak on our graph is not quite as low as it should be, but again, this is most likely due to the wand picking up outside sources of light coming in from the classroom. So these were our systems and how we set up our lab. So for part 1 and 2A, we had the wand of the spectrophotometer and the light directly across from each other with the cuvette in the middle. And then to get the fluorescent spectrum, we had the light and the fluorescein cuvette perpendicular to the wand of the spectrophotometer, and then that's how we got the fluorescent spectrum. Some possible errors that our group may have had is there were some slight inconsistencies in the dye, like concentration differences. And we believe another error in our lab is the outside light sources. The outside light sources could have been in the lights of the room and the laptops being out on our table during data collection. And that is our lab 3, and thank you for listening.